Good morning, students. In our last session, we have discussed about transmission electron microscope. What are the principle of operation? Principle of operation, its applications, and its advantages and limitations we have discussed. So when we compare with optical microscope and scanning microscope, transmission electron microscope, which is having more advantages when we compare, as well as when we see the application, we are having more application with respect to the transmission electron microscope. So in today's session, we will discuss about X-ray diffraction technique. So this X-ray diffraction, which is called as XRD. So by the name itself, it indicates X-ray diffraction. So the X-rays which are diffracted, that is the X-rays which are reflected back. By reflecting or diffracting, we get the analysis of the material here. So when a ray of light, when the ray X-rays which falls on a sample, it is diffracted from that sample, and by the diffraction we are going to see the analysis of that compound or elements, or it may be any of the sample with respect to that. That is nothing but the X-ray diffraction here. So by the based on the scattering of X-rays, by the X-rays by crystal, we go for the analysis of the sample here. So that is called as X-ray diffraction, X-ray diffractometry we call it. So here, based on the angle of diffraction, that is we can see in the figure 1, where the X-rays which are diffracted from the sample here. So whatever we are going to see, those are the molecules or the atoms. What we see from that, the X-rays which falls on these atom molecules, the ray will be diffracted. So we get in terms of the angle there. So angle as well as the d, which gives us the spacing between the space lattice here, and the angle which is indicated by d sine theta. So d sine theta, angle is sine theta, and d is nothing but there we are having a spacing between the diffracting planes here. So that is what we see. So by using this, by using the angle of diffraction as well as intensity of the light or the intensity of the spot of these rays, based on that we see the analysis of the sample here. So based on the angle of diffraction and based on the intensity of intensity of the rays, we go for analysis of these samples by X-ray diffraction. So the Bragg's law is, which is nothing but the scientist by name William Bragg, that is his son as well as father, both have discovered this Bragg's law as well as XRD technique. So for this they have got the Nobel Prize. They have got the Nobel Prize for this one, for both the father and the son who have done the research on this, and they have come up with the X-ray diffractometry. So here these X-ray technique, that is nothing but X-ray electromagnetic rays, what the wavelength we are having, it is of around 0.01 to 10 nanometers. It is having a wavelength of 0.01 to 10 nanometers. That is nothing but 0.1 to 100 angstrom we are having the capacity of that one. So that is high electrons density, which is proportional to higher chance for the finding that count. So here, if we are having the electrons, if we are having the high speed of electrons, or the energy which is having more, the X-ray which is having more energy, so that we can see the diffraction and we get the analysis by this one. So we can see that incident ray which falls on the sample, which is deflected or reflected, to give us the analysis of the compounds, or it may be the elements or the samples we are going to have here. So that is what the technique we are having. So where it is been the scattered, that is the incident rays which will be scattered, as well as which will be emission takes place, that is electrons which emit here, the molecules which when it collides, emission takes place, as well as absorption. By these three techniques we are going to see the analysis of the material here. So microcrystalline powder, so crystalline material can be analyzed, crystalline materials can be analyzed by using the X-ray diffractometry or X-ray diffraction here. So when these high velocity electrons will strike the metal target, then it will produce X-ray here. So in this figure, in the second figure, we can see we are having X-ray tube. We are having a collimator, the X-ray crystal, and from the X-ray crystal, which is diffracted, which are been scattered to get the photographic film here. So the photographic film which indicates the analysis of the sample here. So X-ray tube. So from the X-ray tube, the X-rays are produced. So when high velocity electrons will strike the metal target, so that is nothing. Metal target is nothing but the crystal here. So when the X-rays which are produced in the X-ray tube, the X-rays which are produced here, which strikes the metal or the crystal here. So when it strikes the metal or a crystal, we get the we see the scattering of the electrons or the rays to get the photographic film. So when high velocity electrons will strike the metal target, then it will produce X-rays here. So we are going to have an X-ray produced, and this X-rays, when it is produced, the X-rays which falls on the crystal, when it hits the crystal, or when it passes through the crystal, after hitting towards the crystal, the rays will be deflected or refracted to get the photographic film of the images here. So that is what we are having in the X-ray diffraction here. So we can have X-ray diffraction is a rapid analytic technique. It is one of the rapid analytic technique primarily used for phase identification of a crystalline material. So XRD, which is used mainly for the identification of the crystalline materials. So phase identification of the crystalline material can be analyzed by using this XRD. In most of the cases, XRD is used for the analysis of the crystalline materials, and can provide information of an unit cell dimension. So when we take an example of a crystal, we can find the information regarding the unit cell. So how many atoms are produced, how many molecules are there, and what is its structure. The crystal structure can be analyzed by using this X-ray diffractometry here. So the analyzed material is finely ground, homogenized, and average bulk composition is determined. So composition can be analyzed by using this X-ray diffractometry or X-ray diffraction technique here. So when X-rays which are produced from the X-ray tube, which pass towards the collimator, where the X-rays will be forwarded towards the crystal or the material, which pass over through this crystalline material, it's scattered or it deflect or refract towards the photographic film to get the images or the analysis of the material. So XRD, which is a tool which is used for identifying the atomic and molecular structure. So XRD, which is used for the atomic as well as molecular structure identification in a crystal here. So of a crystal we can identify the atomic as well as molecular structure. Crystalline atoms, which causes a beam of incident ray to diffract into many specific directions. So here when a X-ray falls on a crystal material, the X-rays will be diffracted into many specific directions. We can see in the figure here. So when a ray of X-ray which falls on the crystal, after hitting the crystal material, we see the diffraction or reflection of the X-rays in a different directions. So we are going to see a different direction. That is nothing but when the ray falls on the molecules or the atoms or the molecules, based on the placement of the molecules or the atoms, based on that the X-ray will be deflected to get the identification of those material here. So by the measurement of the angle or by the intensity of this diffracted beam, crystallographer can produce a three-dimensional picture of the density of electrons within the crystal. From this electron density, the mean, that is the portion of the atoms in the the atoms in the crystal can be determined as well as chemical bonding. The chemical bonding, their disorders and other information can be analyzed by the analyzer here. So that can be analyzed by using this X-ray diffraction. So the X-rays which are having electromagnetic radiations, where wavelength in the range of around 0.1 to 100 angstrom, so that we can have a highly images we can be which can use us for the analysis here. So the main principle behind this X-ray diffraction is, in every atom, when we take an example of an atom, the elements are in a layer. So when we take an in every atom, when we take an example of an atom, the electrons are in the layer or in a cell, such as K, L, M and N cells. So here when we take an nucleus, the nucleus will be of positively charged. So that, and the electrons are in the layers. So we can have a K, L, M like this. When we take a K cell to the L cell, or L to M and M to N, when we see this one, the energy which is stored in N cell will have more energy compared to M. And the same thing, M, which is having more energy in the electrons when we compare with the L, and in the same way to the K. So when the atoms are bombarded with an electron which ejects one of the electrons will push us. So when we are going to see a bombarding, the electron will push the another, so which is having more energy. The electrons which is having more energy will pushes the electron which is having low energy here. So when if the electron is having more energy, automatically it pushes the low energy electron here. So when it occurs, one of the electron from the inner cell will go outside here, so that the electrons migrate from the outer cell, that is nothing but N to M, M to L or L to K, like this. The electrons will move in from the outer to the inner cell here to fill the gap. So when, for example, when electron which pushes, for example, the L shell, from the L cell, if the electron pushes to the K cell, automatically it has to fill the gap, so that the electron from the K cell or from the M cell will come and sit towards the gap which we are going to have there. So that is what, by this, filling the gap with higher energy. So when it is done in this way, we can see the X-ray diffraction there. So the quantum of radiation, that is the X-ray which is emitted corresponding to this transition time scale, is approximately, which will be having 10 raised to minus 12 to 10 raised to minus 14. So emitted radiations. So when like this, when we are going to see the movement of electrons from one cell to another cell, or the electrons which pushes the low electron and the gap is filled by other one, when we see this, at that time we see the diversion or diffraction or reflection of an electron from the material here. So that is that rays, the rays which are being deflected will be used for the analysis, or the diffracted ray which gives us the information regarding the emission of the gives us the results in the X-ray diffraction here. So here the X-rays are produced by different ways. So we are having 2 to 3 types of the methods are there for the production of the X-rays. So when we are going to have a production of X-rays, so X-rays are very important here, and it should have high energy here. So high energy production of X-rays are very, very important here. So we are having X-ray tube. So by bombardment of a metal target, so by using the metal, by using the two metals, by using the metal target, by the bombardment of metal target with a beam of high energy electrons, we see the production of X-ray. Here we can see, here we are having the metal, the electrons which will be bombarded in that X-ray tube. So when the electrons which are being produced from the cathode, the electrons which are produced, which will be bombarded with the metal here. So when the bombardment takes place with respect to the metal, the X-rays are produced here. So that X-rays which are being used for the analysis purpose here. So by the second method is by the exposure of a substance to a primary beam of X-ray in order to generate a secondary beam of X-ray fluorescence here. So by the exposure of the substance to the primary beam. So we are having the crystal here. So I have told you the example here, when the beam hits the electron, when the X-ray beam which hits the electron, that is for which hits the electron, so the lower electron, the lower energy electron will be pushed, so that higher energy electron will fill that gap here. So at that time we are going to see the development or the evolution of the secondary X-ray here. So that we call it a secondary beam of X-ray which are being produced. So this is the second method. And the third method, by use of a radioactive source, that is decay process, results in X-ray emission. So by the radioactive materials we can have an emission of X-rays here. So the X-rays are produced whenever high speed electrons collide here. So when we are going to see a collision or bombardment between the electrons which collide with the material target, when it takes place, so by the radioactive source we can have a production of X-ray emission here. So these X-rays which are being produced with an high speed electrons, when the high speed electrons which collide with the metal particle or the metal target, the X-rays will be produced. These X-rays which are used for the purpose of the analysis of the material here. So that is what we are having. So we are having X-ray tube. The X-ray tube, in the X-ray tube we are going to have a metal target as well as high velocity of electrons which are bombardment takes place in this X-ray tube to give us the production of the X-rays here. So we are having we are having the collimator. So collimator, which is nothing but which is a closed metal plates that are separated by the gap, which is used to produce narrow beams. So the X-rays which are being produced, it has to pass. So narrow beams which are being produced, the narrow beams, that is we are going to have a narrow beams, we are going to have a spread beams here. So X-rays which are produced, which have to make a narrow, and it has to pass towards the crystal here. So that is done by using the collimator here. So the monochromator we are having, that is monochromator we are having the absorb the undesirable radiation and allows required wavelength to pass through the material area. We are having the monochromator also. After this collimator we are having the monochromator. So monochromator, which is used to the to make only a single X-ray beam has to pass through the crystal here. So unwanted or the energy which is having less electron, so those will not pass through here. So only the high energy X-rays as well as the wavelength which is having more, those X-rays will be passed through the collimator to get the images here, or through the crystal to get the images. So that is nothing but the filters. So the monochromator is nothing but a crystal here, so which acts like the crystal. So unwanted rays will be removed, and only the required rays, that is which is having high energy, will be passed through the crystal here. So we are having zirconium material. We are having, when we take an example of the crystal, so we are having the chloride, we are having the lithium materials. So these materials which are used for the monochromator here. So in the same way we are having the detectors also. So that is nothing but the photographic film, or it may be the photographic methods or the counter methods which we are going to use. In the same way we are having the another meter, we call it as goniometer. So goniometer we are going to use in the X-ray diffraction. So this goniometer, which is an instrument, it is one of the instrument which is used to maintain the angle and rotate, which is used to maintain the angle and to rotate the X-rays are generated by a cathode. So goniometer, which is used for maintaining the angle as well as to make these X-rays which are produced by a cathode ray tube filter to produce monochromatic radiation, as well as collimated to concentrate and directed towards the sample here. So goniometer, which is an instrument which is used to make the angle to be, or make these rays to be at an angle, and to generate which is generated by the cathode tube, as well as which used for a filter to produce a monochromatic radiations, as well as collimated to produce the concentrated, collimated to produce a concentrated and directed towards the sample here. So that is the for this purpose we are going to have this goniometer. So with the incident ray which falls on the sample, as well as which produce a constructive interference. When when the rays falls on this, we get an interference. So these all are being maintained by using the goniometer here. So goniometer, which is used for maintaining the angle, maintaining the X-ray to be monochromatic, as well as which is collimated and to pass towards the crystal and diffracted towards the photographic film to get the analysis of the material here. So we use for the X-ray diffraction, we use a Bragg's law. So Bragg's law, which is given by n lambda is equals to 2d sine theta. So n is a integer value what we are having, and the lambda is a wavelength of the beam, d is the spacing between a diffracting planes, theta is an incident angle here. So n is an integer, which is nothing but the number of planes or the integers what we are going to have here. So the Bragg's law, which gives the angle for coherent and incoherent scattering from crystal lattice here. So that is for the X-ray diffraction we use the Bragg's law. So by using Bragg's law we can find the crystalline material, as well as which crystalline material it is having, that can be analyzed by using this Bragg's law here. So this is what we are having with respect to X-ray diffraction. So how exactly it works, I will explain once again. So X-rays are generated in a cathode ray tube by heating a filament. So how the X-rays are produced? X-rays are being generated in a cathode tube. I have told this one, which is in a cathode tube, where by heating the filament to produce the electrons here. So by heating the filament, by the bombardment of electrons in this X-ray tube, the X-rays, by bombardment of the electrons, the X-rays will be generated. So these X-rays, which will be having high acceleration, the accelerating electrons will pass towards, or which are accelerating the electrons towards the target by applying a voltage and bombarding the target material with electrons here. So when electrons have sufficient energy due to the bombardment, the electron will have sufficient energy, as well as due to the collimator as well as monochromator, the electrons will have more energy here. So when these electrons have sufficient energy to dislodge inner cell electrons of the target material, so when the high energy, high beam of X-ray or high energy of X-ray, when it hits the element, when it hits the target material, the X-ray spectra are produced here. So when it hits the sample material, the electrons will move from that inner cell, so that the outer cell electrons which fulfill the gap of the inner cell, at that time we see the production or the emission of X-rays, which are in the deflected, which are being deflected or reflected to get the X-ray spectra are being produced. So these spectra consist of several components. So the common being the copper is the most common target material for single crystal diffraction. So in the same way, these X-rays are collimated and directed onto a sample. As the sample and detectors are rotated, the intensity of reflected X-rays is recorded. The geometry of the incident X-ray, or the impinging the sample and detectors are rotated, so that the reflected X-ray is recorded here. So these X-rays which are being recorded, and the geometry of incident beam, so incident beam as well as reflected beam, the angle of reflected or angle of in incident beam as well as angle of reflection, by using the Bragg's law we can find the material which we are having, as well as based on the angle. So when the electrons is of which material, based on that we are going to see the diffraction. So based on that we can analyze the material or the compound which we are having here. So that is what we are having with respect to the X-ray diffractometry here. So the geometry of incident X-ray or impinging the sample will satisfy the Bragg's equation. So constructive interference the peak intensities based on that, based on the angle of incident as well as reflected, or based on the intensity of these X-rays which are being produced. Based on that we can come to know that which material we are going to have, and based on that we can analyze by using the recorded film here. So the detector which records So the detectors which records the process, the X-ray signals, and convert this signal to the count rate, which is then opted to a device. So which will be converted by using the devices which are printers or computer monitor. So based on the geometry of X-ray diffraction, such that the sample rotates in the collimated X-ray beam at an angle. So the X-ray detector which is used to detect the X-rays, so its angle as well as the intensity, based on that we can have an analysis of the material or the sample here. So for this rotation and for all this, we are going to have a gonometer, I have told you. So the instrument used to maintain the angle of and the rotation of the sample, which we are going to have a gonometer for that one to have a rotation here. So these typical powder patterns or data which is collected in terms of 2D sine theta or 2t from angle of 5 degrees to 70 degrees angle that are being present in X-ray scan here. So we can have a angle of 5 degree towards the 70 degree angle. So for all these angles, we are going to have a different element or the powder of compounds we are going to have. Based on that, we can have a analysis of the material here. So that is what we call it as X-ray diffraction. So with respect to this, we see the advantages with respect to other here. So XRD, which is a non-destructive technique. First of all, we have to we should know this one. So X-ray diffraction, which is a non-destructive testing it is, and which is having reliable and powerful tool for crystalline sample identification. So crystalline sample identification can be done by only the XRD. So this crystalline sample cannot be done by using the TEM as well as SEM, or it may be the optical microscope. So crystalline material sample cannot be analyzed by using other techniques. So XRD is only one technique which we are having. Based on that, we can have a sample identification for crystalline materials, so which takes less than 20 minutes to identify an unknown sample here, and which is a simple in sample preparation. We are having sample preparation can be made here by using the different techniques. By using different techniques, we are having, based on that, by using the different techniques, we can have the sample preparation. We can have a sample preparation with respect to this. So in the same way, we can go for a data interpretation, which is relative straightforward. We are having X-rays are the least expensive, the most convenient and the most widely used method to determine the crystal structures. So crystal structure, or when we talk about the crystalline materials, we can have a crystalline as well as amorphous, but for both we can have an determination of the crystal structure by using the X-rays. So X-rays are not absorbed very much by air, so the sample need not be in an evacuated chamber. This is an advantage of this one. So the X-rays cannot be absorbed by the air. So because of that, we are not in a way to have an evacuated chamber here. So the main disadvantage of this one is homogeneous and single phase material is best for identification. So single crystal material or single crystalline material can be analyzed. When we are having when we are having a heterogeneous material, that is when we are having two type of the materials, or when we are having a mixture phase of the materials, cannot be analyzed by using this XRD technique. So less than 5% weight will not be detected here. So we should have a more than 5% weight we have to use for this one. So cannot detect amorphous material. So that is a main disadvantage of this XRD is only crystalline materials can be analyzed. When we talk about the amorphous material cannot be analyzed by using this technique. So at that time we have to go by using the other technique methods here. So XRD do not interact very strongly with lighter elements. So lighter elements cannot be analyzed by using this XRD technique. That is what we are having. So we should have a sodium chloride material. So if we are having sodium chloride material, then we can go for analysis. So the lighter elements cannot be analyzed by using this XRD technique. So X-ray technique can be used only for microcrystalline powder. So when we are having a macro, that is when we are having a bigger size of the crystalline materials, that cannot be analyzed. So micro crystalline powder can be analyzed in this XRD. So the application of this XRD, that is distinguishing between crystalline and amorphous materials. So for finding the crystalline and amorphous material, we can have the XRD technique. So for the determination of the structure of a crystalline materials, we use the XRD. For the determination of electron distribution within the atom and throughout the unit cell, can be analyzed by using this XRD technique. So I have already told, so electrons which are moving from one layer to another, or one cell to the another cell in the crystal structure. So the electron distribution, the atom movement, those all can be analyzed, as well as the movement of this electron from one cell to the another cell, or from one layer to another layer. So the energy required should be more here. The electrons should have more energy, so that we can see the deflection or diffraction of an beam to get analyzed here. So if we are having a less energy, if the electrons is having less energy, then the diffraction will be less here. So we cannot have analyze of that electron or the atom here. So the energy should be more, so that the deflection will be there, more deflection will be there, so that we are having more angle. Based on that, based on the angle, based on the intensity of this electrons, so we can have a analysis of that one. So more energy should be there for the electrons, so that we can analyze the material very easily here. That is what we are having. So determination of the orientation of a single crystal can be done by using this XRD technique here. So this is what we are having with respect to the advantages, applications, as well as limitation with respect to XRD. So we are having one of the video with respect to this. We will watch this, how exactly the diffraction takes place. Please watch this video so to get to know what exactly the XRD technique is. So this is what we are having a technique with respect to XRD. So this XRD technique, what we are having, which is very important as well as useful technique when we talk about the which is having more advantages. So the unknown samples or the unknown compounds or the materials can be analyzed very useful by this XRD technique here. So unknown compounds or the unknown material or the phases which is having within less than 20 minutes, we can go for the analyze by using this XRD technique. So the minimum sample preparation is required for this one. The data interpretation is very simple, so straightforward we are having. So we get the very easily the results or the analysis with respect to XRD technique. So this is what we are having. So we should know that one XRD technique, which is very useful for the analysis of crystalline material. So when we talk about the crystalline material, so crystalline material can be analyzed very easily by using X-ray diffractometry here. So crystalline material where we can have the identification of the phases or identification of the compound unknown material can be analyzed very easily by using this XRD technique here. So that is what we are having a very important technique with respect to the XRD here. So in our next session we will discuss about the different type of the technique that is with respect to these all are whatever we have seen in the last session. So optical microscope, scanning electron microscope, transmission electron microscope, the X-ray diffractometry, these all are with respect to contact type of the techniques what we are having. So contact type of the techniques which are used for the analysis. So in our next session we will discuss about the non-contact type of the techniques which are used for the analysis of the material here. So thank you, students.